Hi there, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at calculating the moment of a force, or in fact, calculating the net moment of several forces. So let me share my screen and we'll get started. Okay, so here's the problem. I'm doing this on my iPad, so I'll be looking down occasionally. But we'll just step through the problem and let's have a look at what we've got here. So we've got a tower crane used to hoist a 2 megagram load upward at a constant velocity. So reading constant velocity, what does that tell us? That tells us that acceleration is 0, so therefore we can use equilibrium. And then we're given the weights, or in fact the masses, of some other components of this crane. So we've got the jib, BD, so out here, and its center of mass is at G1, and we've got 1.5 megagram jib BC, which is out here, and center of mass 0.5 megagrams at G2, and we've got this mass counterweight here at G3 of 6 megagrams. Okay, so we've got all of these forces, and because we know this is being raised at a constant velocity, and hopefully the crane is not rotating and tipping over, then we have equilibrium. All right, so determine the moment produced by the load and the weights of the crane about point A down here and about point B up here somewhere. Okay, so not really an equilibrium problem. When we look at this down here, it's kind of an equilibrium problem. All we're doing in problem 427 here is just to determine the resultant moment caused by these loads. Okay, so hopefully if there is a resultant moment, this support that we've got down here is enough to keep it in equilibrium so the crane doesn't topple over. All right, so let's start solving the problem. So 427 is what we're solving, and how we're going to solve for the moments. Well, we use the moment equation, which hopefully you know is force times perpendicular distance. So most people know that part of it, or just force times distance, that part of the moment equation. However, it's very important to know the full definition, I guess, of this equation. Right? So working out the force, that's usually pretty easy. It's just, force is given, so you put in the number for the force, whether it be in newtons or whatever. But this dimension, or this distance here, this is where people normally get into trouble when they calculate the moment effect of a force. So the full sentence is that this distance is equal to the perpendicular distance from the point where we're calculating moments to the line of action of the force. Right? So the perpendicular distance from the point we're calculating moments about to the line of action of the force. Right? So we'll have a look at how that works as we go through the problem. Something I've done here is to assume all dimensions are from point B. Now, the reason I've had to make this assumption is because this drawing is not that accurate. Okay, so if you look carefully at the drawing, you can see this witness line here for this dimension is a little bit offset from this witness line. Right? So in the absence of any information about that distance between these two witness lines, I'm just going to have to assume that they're supposed to be aligned. Right? So if I was doing this for a client as a real job, then I would go back to them and say, hang on a second, what's going on with these witness lines here with your dimensions? And when I look at student solutions, often I'm very particular, and some would say pedantic, about how you draw your dimensions on your solutions that you present to me. And this is why I'm particular about it, because I'm training you to be intentional and deliberate about what you do, because how you show your dimensions and show where your witness lines are is important, right? it can have a big effect on the problem, right? Or the solution of the problem. Or here I've got to go back and ask the client, if there is one, what is this? What's going on here? Can you redo your drawing, please? Because there's some ambiguity. Or I can just make an assumption, do the calculation, and then send it back to them and say, hey, this is what's going on. But you know, if I was really doing this calculation for a real company, I'd check whether this assumption is correct. At university or high school, if you're doing a problem like this, it doesn't really matter. Just do the calculation, and if you're not sure, just put in an assumption here. All right, so having said that, let's get on with the problem. Now, whenever you're going to calculate moments, if you're doing an equilibrium problem and you're using some of the forces in the x and y direction, as soon as you need to indicate something that's positive, or so in this case, if we're going to calculate moments, we need to know whether the moment is positive or negative. So I've assumed that the moment, assume the positive direction for a moment to be anti-clockwise. Now if we calculate the moment, so this is big M for moments, not little m for mass, so calculating the moment effect about point B. So we're going to add up all of the moment effects of each of the forces that are acting on this crane. So starting from the left-hand side of point B, so the first one I put in here is WG2. So the weight of, it tells me in the question that the weight acts through its center of mass, which is at point G2 here, which is 4 meters away from this witness line, which I'm assuming lines up with point B. Right, so the moment there is WG2 times 4, because we can see the perpendicular distance from the point we're calculating moments about, so we're calculating moments about point B, to the line of action of the force. Right, that perpendicular distance there will be 4. Right, next one. So let's move out to the end here. We've got WG3, and its perpendicular distance is 7.5. Okay, so from point B to the line of action of the force, that perpendicular distance is 7.5, assuming that this witness line is supposed to be aligned with this witness line here. Right, so let's put that in. Now, the other thing that I've done here is to show that these moments are positive. Okay, so remembering our sign convention that we've assumed, anti-clockwise is positive. So if we look over here, this force is pushing down this way. So hopefully you can see that that will tend to rotate around anti-clockwise about point B. Let's go to the next one. So now we've got the weight of the jib B to D. And we're told over here that its center of mass is at G1, and it had a mass of 1.5 megagrams, so acting down here. Right, so its perpendicular distance is this 9.5 that we've got here. So we can put that in. And note now that we've got a negative sign out the front. Okay, so now if we look at this moment about point B, it's tending to rotate clockwise. So if you're not sure, what I suggest that you do is to get your pen or ruler and just pick it up and hold it at the point where you want to calculate moments about, and push down or up depending on what the force is doing. In our case, we've got all the forces pushing downwards on the beam or the crane. So if we push down here and see whether it's going clockwise or anti-clockwise. Right, so on one side of B goes one way, on the other side of B goes the other way. So they must be opposite signs. So this force here must generate an opposite sign moment to this one if we're looking at moments about point B. All right, so let's go to the next one. So we've got the weight of the load acting downwards, and we're told that that's at the location of this crane hook and the load here. So we're given that distance as 12.5 meters. So we can put that into our equation. No other forces acting that we're told about anyway. So now we can calculate the net moment effect about point B of all of our 4 forces. Okay, so now we need to calculate the weight of each of these masses. and we know that the weight is equal to mass times gravity. Okay, so we're given mass in megagrams, and we know grams is in meters per second squared. So here I've said the weight in kilonewtons is equal to the mass in megagrams times gravity in meters per second squared. So normally you're probably used to calculating the weight in newtons. So if we're calculating the weight in newtons, we have the mass in kilograms times gravity in meters per second squared. Yeah. So here I've just said, well, I know that megagrams is 10 to the 3 times kilograms, and 10 to the 3 newtons are kilonewtons. Okay, so I've just used that instead of going to newtons and then having to convert to kilonewtons at the end. So using gravity as 9.81, we can put in our values that we had from the previous line in the equation. Right, so now we've just got the gravity, 9.81 meters per second squared, times the mass of each of the components times their perpendicular distances that we worked out here. So if we put all that in, do our maths, we get the net moment is 76 kilonewton meters. Now, the next part of the problem was to say, determine the resultant moment produced by the load and weights of the crowd about point A and about point B. So I did point B first because that's usually a bit more easier for students to get right. And typically if they try to do about point A first, this is where they start to get things wrong. And this is where it's important to remember the full definition of the moment equation, okay? Especially for what do we mean by the perpendicular distance. If we think about the line of action of this force here, WL say, WL for example, and we continue its line of action down here. So the perpendicular distance between point A that we're calculating our moments about and the line of action of the force, so here's our perpendicular distance to the line of action of the force. And the same with all of the other forces. Okay, so let's take this one for example, over here, WG3, extend that down, and perpendicular distance is that from A. Right, so here you can see why I had to make an assumption about where A is. So similar to what I was talking about before, up here where we've got this little offset. So in the diagram, it looks like A is at the center here, which is where these two, or where this witness line is, but there's no dot here shown for B, and this witness line, as I said, is slightly offset. So again, that's why I say to be careful and deliberate about how you draw your dimensions. Draw them neatly, clearly, and accurately. Having said that about the perpendicular distances, we now should be able to see that the perpendicular distances for all of these forces from point A will be the same as we had from point B, of course making this assumption here. And for that matter, I can see on the drawing there's a little dot just in here. Right? If I put in a C, for example, if I said C, we can say that MA, the moments about point A, and the moments are equal to the moments about point B of all of those forces. We can also say that the net moment about point C is also that same value, 76 kilonewton meters, anti-clockwise, because our value here has come out positive. All right, so let's go to the next part of the question, which was if we now have one of these weights as an unknown. So which one is determine the required mass of the counterweight C, which is this one over here, for the net moment to be equal to 0. So the resultant moment produced by the load and the weight of the tower equals 0. So this is why we have moving counterweights here, so we can balance these loads that we have on our cranes. Hopefully you can see that the equation that we'll make use of is the same equation that we had here. The only difference being is that now instead of having 4 known forces that we're using to calculate the moment, we've now got 3 known forces and one of them is unknown, but we want this moment to be equal to 0. So use the same equation that we had up here, but now we've set this equal to 0. So this is kind of like an equilibrium problem. So just putting in that same equation that we had before from up here, and now we can put in our values, leaving WG3, so the weight of the counterweight here at C, as an unknown. So what weight do we need there to keep it in equilibrium? Just solve this one equation for one unknown, and we get almost 5 milligrams. Because what I've done here, you can see, is I've left out the 9.81 in the calculation here. So because I'm asked for determine the required mass, I've just left out the 9.81 from in front, so I can get my answer directly as megagrams. All right, so that's the end of the problem. Hopefully that made sense. It was a little bit clunky here and there, but anyway, that's it for that problem. I'll see you in the next problem. Bye for now.